Start recording there. Okay, so so this, I said this question is more like to map out our, I can call it more like a course outline, which is very, I don't know, customized, let's say, for our case here. So so the way I was looking at it is for, well, first we'll look at we'll look at bilinear forms, and special cases of bilinear forms would actually be what we call quadratic forms, which are this kind of thing, number 3 here. Then we would look at some kind of connection between it's basically linear algebra applied to graph theory, or graph theory applied to linear algebra. So that's why now we're talking about this aspect of graphs, okay? Graphs, the vertices, edges, kind of thing. By the way, again, I'll keep asking you questions slowly as we move on. Do you guys know anything about graph theory? I mean, apart from what I've just tried to introduce basically. You hear me? I'm asking a question.
On my side, not so much.
Okay,
I don't
fine.
know.
Okay, that suffices, no worries. Okay, fine, no problem. So, so this more or less maps it out. Then I think what I had done in the previous video, which I will go through today, lectures, was to talk about graphs, what graphs are in a very simple way, and then bringing in the aspect of matrices for that, and then touching on what I may call the maximum eigenvalue, eigenvector, maximum degree eigen, this number 8, basically, okay? So straight away, let's just get into business. Let me open the windows that I had. So page 1. So for the lecture for this morning, morning, I call it morning afternoon. I decided to be as basic as possible, and hopefully it helps, yeah? Why is this saying here? Some of these windows, let me close them. Yeah, so anyway, so basics, yeah, for this morning, I just said given any matrix A, hopefully you can see. Now this screen of mine is blocking it, but anyway, hopefully it can be seen. Let me zoom in a bit. Okay, so basics. So you have, in matrix you have in Fn. Fn means that you have a field in n copies of it. So basically an n by n matrix, all right? We talk of an eigenvalue to be, some number such that for some non-zero vector, when you multiply the matrix by the vector, it's the same as multiplying the number by the vector. So that such a number is called an eigenvalue. And the corresponding vector we're talking about is usually called the eigenvector. I mean, as basic as possible, all right? So if you take any matrix, so now some of the properties, again, I'm just jumping more or less. So any matrix I give you, like in this case, I took a 2 by 2 matrix here. And then if I can find some numbers lambda, I multiply by some given vector, the same as multiplying that matrix by the vector, then I would call that vector an eigenvector, and the value the eigenvalue. So some of the properties that are more or less basic are, one, that eigenvalues are the numbers, lambdas, that make A minus lambda I singular. Well, these are matrix. Well, we have a matrix, all right, minus the number, some number lambda, times I is the identity matrix, all right? So singular means that the determinant of this matrix, which I can write this way or this way, is 0. And this equation actually is called a characteristic polynomial. P of lambda equals the determinant of A minus lambda I. That means lambda, some variable, which we can solve for, multiplied by the identity matrix. All right. As we work the properties, we can work with an example. So our example is A. If I pick this matrix, which is a 2 by 2 matrix, 5, 2, 2, 5. Now I form my characteristic polynomial. That means actually how we form this is just taking this guy to this side. You have x minus lambda x. And then you factorize the x, you end up with this kind of thing. A minus lambda times I. In our case, our matrix is A minus lambda times the identity, 2 by 2 identity matrix. So you can see you'll be talking about 5 minus 1 times lambda, so it's 5 minus lambda, and 2 minus 0, and 2 minus 0, and 5 minus lambda. So you have, this is a matrix. 5, determinant of 5 minus lambda, 2, 2, 5 minus lambda equals 0. So this is the characteristic polynomial. And so if you solve for lambda in this polynomial, this equation, you can see when you expand a 2 by 2 matrix, the determinant is, the main diagonal minus, product. So 5 minus lambda times 5 minus lambda minus 2 times 2, which is this equation. And so solving for lambda gives you the eigenvalues. So in our case, here we just have, or in our example, we just have lambda squared. If you expand this equation, you open binomial, you end up with lambda squared minus, minus 5 lambda, minus 5 lambda is 10 lambda, plus this is 5 times 5 is 25, minus this 4 is 21. So this is a degree 2 equation of polynomial, which now you solve. And here, you just factorize. So this is just the factors of 21, whose sum is minus 10, just minus 7 times minus 3. So it's lambda minus 3, lambda minus 7 equals 0. And so the values of lambda are 3 and 7, and these actually are the eigenvalues. Now, unfortunately, anyway, there I scanned my notes here. I didn't scan very nicely because I cut out the finding the eigenvectors. But anyway, at least we have for the eigen. So now, property number 1, 2, number 3. So all the eigenvectors corresponding to lambda form a vector subspace E of lambda obtained by solving the homogeneous system of linear equations whose coefficients is A minus lambda I. So to find now, we found the lambda values. Now we want to find the eigenvalues, or other vectors. So how do you do that? Well, all you do is now you form this equation. E of lambdas, in this case, our eigenvalue is 7. So if I put here 7, I'll have 5 minus 7 is minus 2. 2, 2, 5 minus 7, which is minus 2, 2, 2 minus 2. Now, here I'm saying homogeneous system of linear equations whose coefficient matrix is this one. So now this is the coefficient matrix corresponding to lambda. And so now solving this means that if I pick some two variables, x and y, I'm talking about minus 2x plus y equals 0, and then 2x minus 2y equals 0. Solve that system of linear equations. If you solve, it means that, here if you are applying row operation, so you can say this 2, if I fix row 1, I just have minus 2, 2, 0. Then if I take row 2, I add to row 1, I have 0, 0, 0, which is this. If you divide this guy by 2, you get this. And so here, now here, the way I wrote is just to say y is a free variable, so y can take any value. Then x depends on y, so minus x plus y is 0 means x equals y. So now the eigenvector corresponding to 7, in this case would be the y coefficient is 1 and the x coefficient is 1. Let me see whether I have that in the next slide. Page 1, page 2. Well, no, I don't, but anyway, no worries. So it's just to say that for this case, where is this? Yeah, so for this case, it turns out that the eigenvector corresponding to 7 is 1, 1. That means if you take this matrix of ours, you multiply by 7, it should be the same as 7 times 1, 1. If I take lambda times the eigenvector is 1, 1. In fact, as we work this, you can be, you have a piece of paper there, you can even do the verification. So 1, 1, you multiply by 7, you get 7, 7. If you take our matrix, which is this one, 5, 2, 2, 5, you multiply that by our vector, which is 1, 1, what do you get? If I put 1, 1 here, I'll have 5 times 1 plus 2 times 1 is 5 plus 2, which is 7, and 7. So it will give us actually what we expect. So A times 1, 1 is the same as 7 times 1, 1, which means that the eigenvalue 7 corresponds to the vector 1, 1. Hopefully it's clear. I don't know, in as much as are we together?
Question.
Yes.
Question. So you see, okay, I've understood that when now I have my eigenvalues,
Yes.
like the two of them.
Yes.
So I'm having an issue where now you're getting the eigenvectors. So you
Okay.
said you're going to substitute the E lambda, you're calling it the vector subspace.
Yeah,
Or
this is a space actually. Yeah, this is an eigenspace of 7.
so you're going to do like E lambda is equals to then you replace the lambdas, the value, maybe because here you got 3 and 7. So when we started 7, you start replacing now from where it was 1, where it was 5 minus lambda. So you're putting 5 minus 7. We
Exactly.
get now minus 2. Oh, and then 2, and then 2, and then 5 minus 2. This 0, 0 part, where did you get it? The one next there?
Okay, good question. Actually, thank you very much for feedback, and actually what I wanted. That's why it's better to have a class and a video being shared because you cannot respond. Very good. Yeah, so thank you very much, Jessica. Now, actually, yeah, so the point is here we're saying that once you get the eigenvalues, this is how you get it from the characteristic polynomial. That's clear. Now, the eigenvectors, to get them, you're using, for each lambda value you get, you will solve a system of linear equations whose coefficient matrix is m minus lambda I. So like the way you have said, your meeting will end in 10 minutes. Okay, no problem. We will start another one. Probably it's because I've been on for a while. Anyway, that would be good for us to take a short break. Now, so 5 minus, so like you've said, so now the coefficient matrix for the system I will form is this minus 2, 2, 2 minus 2. Now, so in a sense, like I have this matrix 2 minus 2, or rather minus 2, 2, rather minus 2, 2, 2 minus 2. Then this, the system now I'm forming, I have two variables, x and y. All right, I'm just calling them two variables since they're 2 by 2. So the system of linear equations I form, when we say homogeneous, it means that we normally equate it to 0. So in a sense, I'm forming a system where the coefficients are this. So this first equation would be minus 2x plus 2y equals 0. And the second one would be 2x minus 2y equals 0. Solve that system of linear equations. The values of x and y, all those values would form the eigenspace corresponding to 7. So one of the vector representatives, if you pick any vector in this space, you actually get an eigenvalue corresponding to 7. So I hope that is clear. So that now you proceed by doing what? You now solve the system. So how do you solve a system like that? Minus 2x plus y equals 0 and 2x minus 2y is 0. It means that this equation is just a multiple of the second equation, right? That's why
Question.
yes.
Sorry. Please say it slowly. That part for minus 2, I'm trying to write it so that I'll
Okay.
calculate as. Oh.
Okay. So the system now you're forming is this part, is 2
Uh,
minus 2x plus
uh-huh.
2y equals
Uh-huh.
0. That's equation 1.
Uh-huh.
And then equation 2 is 2x
Uh-huh.
minus 2y equals
Uh-huh.
0. So you have two equations. Okay?
Yes.
So now solve those equations. How do you solve those two equations? Well, one way is just, what you used to do, like, I can say, for this particular case, you can see that the first equation is minus 1 multiple of the second equation, right?
Yes. Yes.
So that's how now this becomes 0, 0, 0, really, right?
Okay.
And
Uh-huh.
then the first equation, if you divide by 2, you're talking about minus x plus y
X
equals
plus
0,
Y.
right?
Yes.
Which is translates to basically x equals y, right?
Yes.
And
Yes.
so now from here, we can say that really
Uh-huh.
the space of 7 is all those values of x that are equal to the values of y.
The space of 7.
The
Sorry.
eigenspace
Uh-huh.
is all those values of x that are equals to y, because we have solved our equation and it turns out that the values of x should always be equals to the values of y.
Mm. So I go now replacing. Sorry.
So if you write down, let's say you are
Mm.
writing down the solution for this, the eigenspace, you will write down the values
Yes.
of x are, I just say you will write like a pair, x, comma, y. The values of
Mm-hmm.
x that are going to be in this space are basically when x equals y or y equals x.
Yes.
For example, when x is 1, y is 1. When x
Yes.
is 2, y is 2. When x is 3, y
Yes.
is 3. When x is 0, y is 0. So that means this actually the eigenspace of 7 is all those pairs of values of x and y that are equal. Make sense?
So you sorry, you have understood that place was 0, 0.
Yes.
Okay, so at the end now,
Eh.
so what I've not understood now that part where you get what are you going to be now your eigenvectors
So the
after this?
eigenvector, so now you have understood the solution to this, right? The
The way we are
solutions is
going
this,
to
yeah. So now
uh,
you pick one representative vector. For example, I can just pick when x is 2, what will be the
uh
value of y,
to oh
right?
x is equals to y 2.
Yes. So if x is 2, y is 2, right?
Yes.
If x
Yes.
is 3, y is 3, right?
Yes.
So the only condition is that we say that we don't want, let me see whether I can, we don't want our vector to be 0. So you just pick any non-zero. So I can say, for example, the x is 1, y is 1. So, in fact, it can be seen. Here it is. So
You
the
can now
vector
see.
corresponding to 7 is 1, 1. I mean, I've picked 1, 1. I could have picked 2, 2, 3, 3, any representative vector. So the eigenspace of 7, the eigenvalue is 7, right?
Uh-huh.
The eigenvector corresponding to 7 is 1, 1. So
So if somebody writes 2, 2, it's still a
it's
right
still
answer.
okay. It's still a right answer, yes.
Oh, and
Yes.
you're
Yes.
just to clarify,
Uh-huh.
this 1, 1, we
Yeah.
got it because after solving those two equations
Yes.
where we were left with minus x plus y is equals to 0, so that we ended up getting x is equals to y.
Yes.
And sorry, another question.
No,
This
don't be sorry.
minus,
Just ask.
sorry, minus 1, 1 up there,
Where now?
um,
Here.
there on your right,
Here.
chini on
On
your
my
right,
right. Uh-huh.
after the 0, 0,
Yes.
that
This.
that one.
Uh-huh.
Where did we get? I remembered where we got the 0,
Yes.
but I'm up there where we got minus 1 and 1.
Uh-huh.
Was it? Uh,
Because the
mm,
first equation is minus 2x plus 2y, right? Equals
yes,
0. If you divide
yes.
by 2, what happens to the equation?
You get minus x plus y.
Y. So the coefficient
Uh,
is minus 1 and 1.
Minus 1. Oh, and then y is okay, okay,
Yes. Yes.
okay, okay, okay. And
Good.
then
Uh-huh.
um when I was learning about those eigenvalues,
Yes.
so the speaker said
Yeah.
that part for where we do the okay, he just said before when you're getting the eigenvalues, when
Mm-hmm.
now this part where it's therefore 5 minus lambda 2, 2, and then 5 minus lambda is equals to 0. He said, take the determinant of this matrix and set it equal to 0. What the and okay, where you've pointed, he
Mm-hmm.
said, take the determinant of this matrix
Mm-hmm.
and set it equal to 0. What
Mm-hmm.
does determinant of this matrix mean? Or
Okay. So determinant. Well,
uh,
okay. Let's just pick a matrix. This is a matrix, right? 5,
yes,
2, 2, 5. What is the
yes,
determinant of this matrix? The determinant is just this, the main diagonal, basically 5 and 5. So you multiply 5
uh-huh.
times 5, you get 25, and
Oh,
then minus 2
oh.
times 2.
Oh, okay.
Aha.
Okay.
So now with
Thank you.
that, you just now say determinant of this, which is translated here was
Good.
minus this times this is this
This
times
times
that
this.
minus 2 times 2, like that.
Uh,
Make sense?
okay. Yes.
Very good. So now the same thing you have asked, and then it turns out actually we can see, is now for the eigenvalue for the eigenvector for 3, right? So we do the
Oh,
same thing
yeah.
we've done. So the eigenspace for 3, now we will set 3 here. We have 5 minus 3, we get 2, and then 2. Then 5, 2, and then 5 minus 3, you have 2, 2, 0,
Two, two,
and
two,
then 2,
two.
2, yeah, exactly, right?
Uh-huh.
And then the same thing we've said, now we have the same equation repeated because this 2x plus 2y is 0,
2x
and 2x
plus
plus
2y.
2y is 0. So really, if you subtract the first equation, you just end up with 2x plus 2y is 0, and then 0, 0, 0. Sour.
Yes.
And then
Yes.
now if you divide by 2, the first one, you get 1, 1, 0.
1, 1.
So now here again, we say the same thing we said, that it turns out that, I mean,
The vector.
x plus y is 0, so that means x is minus y, or y is minus
Yes.
x.
Yes.
So if you are to write down the solution, this eigenspace, you would say this turns out to be all those values of x that are the negatives of y, or all those values of y that are the negatives of x. Okay?
Yes.
So I pick a representative vector, I'll just say minus 1, 1. Because
One.
when, and this now corresponds to, so the vector corresponding to 3 is minus 1, 1.
Minus 1, 1.
Nice?
Yeah, question.
Aha, good.
So
Mhm.
yeah, Amanda, so will it be okay to even write 1 and minus 1 below?
Yes, it's okay.
Oh, okay.
Yes, yes, yes.
Okay.
So you just pick a representative vector.
Okay.
So how many minutes do we have before this video goes away? Maybe 5 or less. Anyway, something like that. Okay, so far so good. Sawa. So,
Yes.
I mean, now more or less we've reminded ourselves, when you have a matrix, you can always find the eigenvalues.